and usually we call it damped or exponential decay because the sigma, the exponent, parameter of the exponent, or the coefficient at sigma t, is usually negative. Okay, we know that if that coefficient sigma was positive, then we would have a problem because the amplitude would rise to infinity as the time goes. So in normal practical situations, sigma, that exponential coefficient is always negative. So as I've already said, you can now set sigma and omega to 0, and you can express a DC voltage or DC value using that general expression, exponentially decaying sinusoidal function. When sigma is equal to 0, e to sigma t is of course 1, and we have just a normal sinusoidal signal with some frequency and maybe a phase. We can also imagine a situation when sigma is not 0 but omega is 0. Then of course Vm times cos theta, which is the angle, is a constant number. We call it V0 here, and we have an exponentially changing, varying, which might be decaying or increasing depending on sigma signal. So we can combine, depending on the values of sigma and omega, we can create different types of signals from using one expression, one general expression. So we've seen already this kind of expression when we had the magnitude and e to j omega t component. We already seen this without j, of course, but now if we add the complex or imaginary rather number, we can create something that we call complex frequency. So complex frequency is the sum. It's a complex number, sigma plus j omega. So far we looked at frequency in frequency domain. We looked at that function that had all functions that had j omega in it, and so sigma was 0. But now we can actually add that sigma and see what will happen. So certain things I want to skip here. We can start by declaring a function k e to st. K is bold here because it's a complex number. S is also bold because it's a complex number. So we have something that is very similar to the real expression, but it has complex constants here. So now, if we want to get a constant voltage, we may use that function with exponent equal to 0 and k being a real number. Okay? And so on. We can, using this notation, we can create again all possibilities that are available here, like DC, pure sinusoidal signal, pure exponential signal, and combination of exponential and sinusoidal, which is the exponentially decaying or varying signal. So there are some quirks here, mathematical quirks, which we will not go into because they are not at this point that very important. What is important is that we can, depending on a particular type of signal, we can easily define the elements of its complex frequency. Okay, so if we have a signal which is a constant, our complex frequency is just 0. That's the easiest one. If we look at the exponential signal, our complex function is just real, and the imaginary part is 0. So you can see now that the imaginary part is responsible for the actual sinusoid or sinusoidal behavior of the signal. And the real part will be responsible for the rate of decay. Now for purely sinusoidal signal, of course, as I said, we skip the maths, so I don't want to spend time on explaining why all that is here, but we normally drop the second solution. We only look at the first solution, first root here, which is just j omega. So for sinusoidal signal, we have our complex frequency, which is purely imaginary. We're already familiar with that. Okay. So now if we have a most complicated signal, which is exponentially decaying sinusoidal signal, both real and imaginary parts of our complex frequency are present. They are not 0. So we have real part, which is responsible, as I said, for exponential part of the time domain, and imaginary part, which represent the frequency of the signal. So we can, of course, go backwards. If we know the complex frequency, we can reconstruct the actual signal. So suppose now, we'll come back to the S in a moment, but suppose now that we have a system, linear system. It all applies to linear systems only. So if we have a linear system, and if our input, or forcing function, is exponentially decaying sinusoidal function, this is generalized, of course, so now but you can guess now that if you choose properly sigma and omega, this expression actually can give you all 4 possibilities. DC, purely exponential, purely sinusoidal, and exponentially decaying sinusoidal. So now we can again skip the maths here, and let's see how we actually apply it in calculations. Or maybe before we go into that, we'll see how we do it in sort of a long way in the time domain, and then we'll do the same in the frequency domain. So suppose that you have a circuit like this, nothing special, RLC circuit, and V of t is now the full exponentially decaying sinusoidal function. And we want to find the response. Okay, and only we are interested in the force response at the moment. We know that the force response of any linear system has exactly the same form as the forcing function. So if your forcing function is DC, constant, the force response will be constant. If the forcing function is sinusoidal, the response will be sinusoidal with the same frequency, and so on. So we know what to expect.